The next speaker is Dr. Antonio Iannitelli. He's from the University of D'Annunzio of Chieti. He is a PhD and now he has a postdoc in the University of D'Annunzio. He was a visiting scientist in Geneva, Copenhagen and Pittsburgh, and his research is mainly involved in the study of new strategies for targeting of L-dopa in the therapy of Parkinson's disease, and in the research of new drugs and methodologies for drug delivery in the treatment of neurodegenerative diseases.
Thank you, Dr. Marianici, for introducing me. So, neurodegenerative disease have long been viewed as the most complicated and enigmatic issues in medicine. However, it's clear now that the major processes involved are multifactorial in nature, and they are caused by genetic, environmental, and endogenous factors. Although each disease has its own molecular pathways, some general processes might be recognized. They include protein misfolding and aggregation, oxidative stress, mitochondrial dysfunction, how we have seen in the past days, and neuroinflammation, all occurring concurrently. Concerning oxidative stress, reactive oxidative species are normal products of normal aerobic metabolism, and they can play a dual role as beneficial but also as deleterious species, according to their concentration. Oxidative stress occurs when the production of free radicals is in excess of the antioxidant defense, and it can initiate a cascade of events leading to mitochondrial dysfunctions and neuronal cell death. So, because of the well-known role of oxidative stress in neurodegeneration, it seems reasonable to propose that exogenous antioxidants could be useful in reducing the oxidative damage. Indeed, antioxidants of a widely varying chemical structures have been used and investigated as potential therapeutic agents, and have shown slightly ameliorating effects on the progression of several neurodegenerative diseases. But however, their use in therapy is limited mainly because of their marginal ability to cross the blood-brain barrier. Among the several antioxidants proposed, lipoic acid is a promising candidate and has been used and investigated in clinical trials to prevent Alzheimer's disease. Lipoic acid is a dithiol compound that readily crosses the blood-brain barrier and accumulates in all neuronal cells, where it is reduced to dihydrolipoic acid, the active compound responsible for most of the beneficial effects, such as the chelation of metal transition in biological systems, the scavenging of reactive oxygen species, and the increase of acetylcholine production. Thus, because of its multiple effects, we have decided to use lipoic acid as a privileged structure to which link selected pharmacophoric groups in order to hit the different targets of diseases such as Parkinson and Alzheimer's. Thus, the first aim of our work was the design of a series of multifunctional co-drugs where dopamine, or L-dopa, was linked to lipoic acid by a biocleavable amide bond in order to overcome the pro-oxidant effects associated with the L-dopa therapy in Parkinson's disease. On the other side, because current evidence supported the idea that non-steroidal anti-inflammatory drugs might protect against the development of Alzheimer's disease, we had as second purpose the aim of the design of a series of lipophilic bioconjugates obtained by joining lipoic acid and ibuprofen via a series of diamino linkers. These new entities, combining the scavenging of reactive oxygen species with the anti-inflammatory capacity and the allosteric gamma secretase modulation, might allow the targeted delivery of the parent drugs to neurons where the cellular oxidative stress and the neuroinflammation, together with the production of the A-beta amyloid proteins, seems related to the disease. The first class of compounds possessed good lipophilicity, significant stability in simulated gastric and simulated fluids, and were able to release dopamine or L-dopa and lipoic acid in human plasma after enzymatic hydrolysis. The tested compounds were also able to protect against the oxidative stress deriving from the auto-oxidation of dopamine. And this suggests us that the potential advantages of using 1 and 2 rather than L-dopa in treating Parkinson's disease. And moreover, since the progression of the disease leads to a narrowing of the therapeutic window for L-dopa over time, we are currently developing, in collaboration with Professor Henning from Utrecht University, a colloidal drug delivery system loaded with our bioconjugates, able to provide a continuous dopaminergic stimulation, more similar to what happened in the normal and health patients. However, in this presentation, I would like to focus your attention on the results obtained with the second series of bioconjugates, the lipoic acid ibuprofen bioconjugates. The lipophilic parameters were determined using the HPLC retention times and the ACD log-P software. As expected, the lipophilicity values were favorable for a significant blood-brain barrier crossing with respect to their parent compounds, especially the bioconjugate 5. The new entities were extremely stable in buffered solution, the simulated physiological solutions, and a slow bioconversion to ibuprofen and lipoic acid was observed in rat human plasma. Half-lives exceeding 115 minutes indicated a high resistance to peripheral enzymatic degradation, and notably, these new entities underwent to a more rapid hydrolyzation in rat brain homogenate than in rat serum. And this let us suppose that these new entities might allow the potential targeted delivery of the parent drugs to the neurons. We also assessed the free radical scavenging activity of the new entities with two different in vitro assays, the DPPH-HPLC method and the deoxyribose oxidation method that we will see later on. The data demonstrated that, unlike ibuprofen, that is not shown in the graph, the radical scavenging activity of the bioconjugates increased with the concentration. Moreover, the hydrolipoic acid and lipoic acid were stronger free radical scavenger than, the hydrolipoic acid was a stronger radical scavenger than lipoic acid, and the bioconjugate 5-7 were stronger than ibuprofen. Furthermore, lipoic acid and the hydrolipoic acid here displayed an antioxidant activity, while ibuprofen a pro-oxidant activity. As expected, our bioconjugates modulated the pro-oxidant activity of ibuprofen with their ditiol moiety deriving from the lipoic acid moiety in the molecule. In this study, we also investigated whether bioconjugate 5 can improve learning and memory impairment in an A-beta-40 intracerebral infused Alzheimer's disease rat model. All rats were trained for their behavioral study in an 8-arm radial maze, and working memory errors and reference memory errors were recorded 1 and 2 months before the surgery for the infusion of A-beta-40. The infusion of A-beta led to a progressive cognitive deterioration affecting both reference and working memories. The decrease in working memory errors after treatment with ibuprofen and bioconjugate 5 during the same period of A-beta-40 infusion was due to a positive effect of the anti-inflammatory and antioxidant agents. However, it must be said that there were no significant difference in reference memory errors during the first month of treatment. This data demonstrate that the treatment with combined anti-inflammatory and antioxidants drugs provide an effective protection against cognitive deterioration, suggesting the significant neuroprotective effect of bioconjugate 5. These data were supported by the histochemical findings. In particular, here we can see A-beta-40 injected cerebral cortices treated with ibuprofen or bioconjugate 5 showed fewer plaques within the capillary vessels, and in particular, A-beta-40 protein was less expressed in bioconjugate 5 treated than in ibuprofen treated cerebral cortex. Basing on these promising results, we are currently developing a colloidal system for parenteral delivery of bioconjugate 5 in order to achieve an extended release of the drug, thus reducing the subcutaneous number of administrations. We formulated bioconjugate 5 loaded PLGA nanoparticles using the nanoprecipitation method reported by Fini. And among the several formulations realized, the PLG7L resulted the best one. The preliminary data for the in vivo releasing indicates that there is an extended release of the bioconjugate 5 from the particles, but the evaluation of the best releasing profile for the in vivo studies is still in progress. We have to optimize all the systems. So, concluding, we reported the design of new bioconjugates obtained by linking a powerful antioxidant, lipoic acid, with an anti-inflammatory agent, ibuprofen. Moreover, the new entity displayed a good physicochemical property and good stability in gastrointestinal simulated fluids, releasing lipoic acid and ibuprofen in human plasma after enzymatic hydrolysis. And in particular, bioconjugate 5 displayed neuroprotective effects against the cognitive dysfunction induced by intracerebroventricular infusion of A-beta rats, thus suggesting that the bioconjugate 5, combining both antioxidant and anti-inflammatory properties, could represent a useful multifunctional agent for controlling Alzheimer's disease, induces cerebral amyloid deposit and behavioral deterioration. At the very end, I would like to thank our research group in Chieti, then Professor Cataldi and Dr. Zara for the histochemical studies, and Professor Cantalamessa and Dr. Nasuti for helping us with the pharmacological tests, and of course all of you for the kind attention. Thank you.
Thank you, Dr. Iannittelli, for your interesting presentation. Now there is time for questions.
Yeah, one. The first one is you planned this conjugate for oral delivery, I think.
Well, we...
which is the solubility of ibuprofen, for example?
You mean the first series of the...
Oh, the ibuprofen, this one.
Okay. For this one, we use subcutaneous injection, because as you can see, they are not very soluble in water.
In fact, it's not.
And the log P is, well, good for a blood-brain crossing. We are below the 5.
My wonder is, in terms of stability, of course you found that in the blood there is no degradation, is an amide. It was expected.
Yes.
Then you tested the brain cell homogenates, but have you, for example, tested the liver homogenates? I mean,
no.
Have you some idea of the stability in the blood, in the circulation?
We didn't test in the liver stability.
This
is an...
of course, in the blood there are amide groups, so...
Yes, yes, they
amidases are at a low level.
But we tested the plasma stability. Of course, in liver there are more and more
enzymes. Should be interesting.
This is a next step, because we are, of course, validating the colloidal systems.
There is
So probably I missed some part of your presentation, but do you have an idea about the biodistribution of these bioconjugates? Because we did together with Rosario some studies with the similar bioconjugates.
Yes,
yes, probably you saw them.
Yes,
Rosario published that, and the problem it was that we saw that soon after injection, our conjugated, the conjugated Rosario synthesized, which were a bit different anyway by this one, disappeared immediately from the bloodstream, and the reason was not because they localized in some specific organ, just they probably interacted with endothelial cells or a number of structures. So I don't know if you have an idea or hypothesis to verify, or how do you think to move in this way?
Well, we, of course, taking into account the high lipophilicity of the bioconjugates, hypothesized a high protein binding and diffusion in the endothelial cells. But we had to make a decision. As you can see, the in vivo experiment are very long and time consuming. So we couldn't sacrifice as much as animals you made in your paper. So we had to we wanted first to check if there was a neuroprotective activity, and this could be a second aim of our work, because taking always in account the development of the colloidal system.
Thank
so
you.
We will assay in the next.
Could be a solution for this concept.
Yes. So that's okay.
Thank you again, Dr. Iannittelli.